Hi there, my name is Shelton. I'm a Master's of Applied Science student at St. Mary's University in Halifax. My supervisor is Dr. Shannon Sterling from Dalhousie and Dr. Kathy Conrad from St. Mary's University. So today I'll be talking about the accuracy of water monitoring data, and it'll be two parts. One is the Cure H2O project, and also my own research, which is looking at the reliability of citizen scientists, so local citizens collecting monitoring data, particularly water monitoring data. So as an outline, Cure H2O, I'll be discussing the challenges and benefits of citizen science, the community-based environmental monitoring network, which I'm also a part of, Project WebPro, and then going on into my research, the reliability of citizen science. So as an introduction to Cure H2O, it began last year in March, which was formed from the funding received from the Community University Research Alliance, which is a shared-funded program. And the total purpose of it was a three-part program, particularly a training program that was implemented to address standardization of water quality protocols and also addressing standardization of equipment as well. Having data integration with decision-making, and also basic theoretical research would be the guiding component of the project. So what are the benefits of citizen science? Often this can be used for a range of projects. You're looking at birds, you're looking at climate change, and now also water quality. They're often ideal candidates because they have personal interest in their local environment, and also the United States Environmental Protection Agency uses a lot of citizen science data in their biennial reports. But they also are facing challenges. Often some of the major things that have come up is monitoring for the sake of monitoring. This can lead to volunteer lack of interest and also lack of funding. So with government funding cuts, we can have data fragmentation. And the last 2 points, lack of participant objectivity and accuracy, and also lack of integration with decision makers are the two aspects that I'll be looking at. So supporting programs of Cure H2O, as I mentioned, there's a Project WebPro, which involves a training course and also standardization of equipment, and also the community-based environmental monitoring network, which is CDEMN for short. So the CDEMN, this is what has been basically the beginning stages of Cure H2O. It's an NGO that's housed within St. Mary's, and it provides equipment free of charge to many monitoring groups in Nova Scotia. And it also provides expertise and kind of helps them develop their own monitoring programs. So through this work, we discovered that there was kind of this lack of integration decision making, that often there was a lack of comparability between community groups because they're using different equipment, they're using different protocols and standards. So through this, we identified the need for a new project, Cure. So what was the challenge? To build the capacity and credibility of community-based water quality monitoring efforts and develop these partnerships that are kind of key with government, so that we can have this monitoring data being used in decision making. So the strategy that was devised will have the three following components. So there's a development of a standardized monitoring toolkit and an online training course. This is Project WebPro. And also development of a centralized database so that all of the monitoring data for community groups in Nova Scotia will be placed in one repository, and then this information will be available to government. So the Project WebPro training program had the purpose of building the capacity and credibility of community-based monitoring efforts. So we had a development of partnerships with government to make sure that what we're providing is accurate standards, protocols that they follow themselves. And there's long-term goals of having this be nationally and internationally used. So we have some international partners in Bardia, Nepal, and also in the Gambia, West Africa. And this is a 5-year project, and so the training program will be in the first 2 years piloted, so this is the second year. This is an example. There's photos down below of basics of freshwater systems, mainly surface water. We're looking at water quality monitoring parameters, guidelines for protection of aquatic life, monitoring program design, sampling methods and techniques, and then also quality assurance, quality control. So the Wet Pro Field Kit had the training course and the accompanying toolkit were developed to address the lack of consistency. So there was a lot of consultation with Environment Canada and Nova Scotia Environment to make sure that we're choosing the proper equipment, and it was developed through the support of SSHRC, St. Mary's, Nova Scotia Environment, and the CEMN. And the overall goals had high scientific accuracy, be user-friendly so that someone without a scientific background could be able to use it and still have a certain level of accuracy. And also be cost-effective because we wanted this to be at a community level. So this kind of leads into where my research began. We've noticed that the lack of data with decision-making was often because even though there's a value to citizen science, there's not a level of accuracy that's kind of stated for water quality monitoring. So I looked at comparative studies for volunteers versus professional. Often its majority was comparative research with biological indicators such as macroinvertebrates. When the studies did involve water quality, they were often water samples rather than field measurements. And also there was a variability of water quality parameters. So certain parameters that you choose have a higher range of variability, some are more stable. And sources of error. So many of the sources of error that were kind of shown in the research was that procedural differences when we were looking at physical habitat data was one of the main sources. And often this is done so that volunteers have an easier method that they can follow. However, it can also lead to errors, and also small scale spatial and temporal differences were also noticed. So primarily with water quality data, you have to make sure that you're sampling the exact same location at the same time, or else you're going to have a variance that doesn't have anything to do with what the accuracy of a volunteer is. So in order to increase accuracy, water quality samples must have a simplified methodology. And overall, they show that trained volunteers can collect reliable, specifically biological data. However, there are certain aspects of the program that professional scientists need to identify and address, which is particularly data interpretation. So the knowledge gaps that we found, there were limited comparative studies with water quality, so we don't actually have kind of a baseline data to show whether volunteers and professionals are comparable. Previous studies also used historical data, which means that there was a lack of standardization with the time that the water samples were taken, the equipment, and where they were sampled. But despite the literature indicating that there's a high value for citizen science, there's still this concern within the government saying whether or not there is a high credibility when you compare it to professionals. So the setting that I was looking at was in Nova Scotia. Basically, we need to have an assessment of ecosystem health, but it needs to be low cost, and such as a volunteer program. We have over 60 community groups collecting monitoring data. Some have decades worth of data, but it's not being integrated. So there's the problem was limited water quality comparative studies and this concern that it's not comparable. So the solution was to collect side by side a professional and a volunteer, and we standardized training. We had the volunteer actually conduct calibration and have the same location, time, and equipment. So the research questions we looked at was, do volunteer citizen scientists collect data that is significantly different from the data collected by professionals? And what conditions would citizen science collect the most reliable data? So we're trying to highlight what parameters would be the most reliable so that we can create a monitoring program that would be the most effective for integration with government. So my hypothesis, data collected by citizen science will be within the instrument accuracy specifications, and also the main source of error will be from the instrument variability and calibration procedures. So So the study design, there were 25 volunteers and 2 treatment groups, the volunteer treatment group and professional. So they're collecting real-time field measurements. They'll be side by side in the stream, and each volunteer will collect a sample at up to 10 transects. So each transect is referred to as an event, and just so this is an example of the where each sample will be taken. Total sample size, we're taking 250 water quality data sets with each treatment group collecting for a total of 500 water quality measurements. What we'll actually be collecting. So the water monitoring data that we chose was dissolved oxygen, temperature, pH, and conductivity, basically trying to find a few basic water quality parameters to be the most cost-effective way to design a program overall through the province. These were kind of highlighted as the most generally used in Nova Scotia, but also had the higher range of stability. And then just basic site descriptions and channel measurements as well. So the methodology, like I said, we standardized the equipment. So we used a YSI Professional Plus, which is in the wet pro toolkit, a flow probe for velocity. We had a standardization of calibration procedures, which, as I mentioned, the volunteer also went through. And they went through online training and field training for sampling and calibration procedures. So it began in May of 2012 and will continue into the fall. And so there was a range of environmental characteristics where we sampled. So there was 8 counties, and it's all across Nova Scotia. This first table looks great. There's a lot of information here, but basically just indicating that the USGS, United States Geological Survey, what is the range that they'll accept. So if a professional is collecting at a certain range, you can have for temperature, we have plus or minus 0.2 degrees Celsius off. So this is kind of the way that you're following for volunteers, and to look at the acceptable data accuracy range. And table 2 just refers to the stabilization when you're in the field, what kind of variation would you expect once you're there. Preliminary results, table 3 and table 4 are just an example of one site that we selected and how it's broken up for each parameter and how they're collected within the same time frame. Again, preliminary results, we had some comparison of water temperature. So at each event, a volunteer and a professional collected data, and so there were 2 instances where at 7 and 6, where it was outside of the 0.2% accuracy range. And overall, out of 150 samples, we have 9 events out of range, but otherwise we have 141 within. And so overall, the lessons learned, there will be limitations with scheduling. Often volunteers do this on their own time on the weekends, and so there's issues there. For training, specifically with highly technical instructions such as calibrations or field sampling, it has to be done for many different learning styles. So this is something that we kind of have to address also in the online training. Oh, and expect chickens. You never know what you're going to find on the side of the stream, and they follow you through the whole thing. So, continuation of analysis. So I will be continuing to do data collection until the fall. There'll be questionnaires to kind of look at the qualitative analysis and determine if previous background and previous training has anything to do with the correlation with their accuracy. As many volunteers, they actually have personal interest in this field. They might even be professional scientists in their own right. So we're trying to also look at that. And just analysis of results, which should be really fun. Thank you.